today we are going to discuss some topics in preliminaries. So, again the topics include some from analysis and some from linear algebra, etc. So, specifically, so let me mention what I am going to do in this 1 hour. First discuss linear dependence and independence of functions. So, that is very much used in the study of linear homogeneous equations later. So, linear dependence and independence of functions. And then we will also discuss the calculus lemma, which is going to be used in a qualitative theory of differential equations. So, this is one specific calculus lemma. There are many things in calculus, but this what I am going to state about this lemma. And then an important formula which is referred to as differentiation under integral sign. So, this is going to be used, for example, in the study of boundary value problems using green functions under an integral sign. And then we will also use we will also learn something about Taylor's formula, which will be used in the linearization theory of nonlinear equations. Okay. And finally, we will also discuss some fixed point theorem and some related issues. So, this is referred to as Banach fixed point theorem. So, we are going to learn about that. Okay. So, let me start with linear dependence and independence of solutions. For that, so let I be a non-empty interval in R. Okay. So, this can be finite, infinite, does not matter, and put x is equal to. So, this is collection of all functions, real valued functions defined on the interval. As of now, I am not putting any structure on the solutions, continuity or differentiability, anything. So, they are just functions. Okay. And it is easy to check that x. So, check x is a real vector space. So, if we are given two functions in this set x u1 u2, then I can define their addition and multiplication by a real number, and if u belongs to x, minus u also belongs to x, and minus u is the additive inverse of u, and the identically 0 function is the 0 in this vector space. So, this is not difficult to check that x is a real vector space. So, we are going to discuss what is meant by linear dependence or independence of two elements in this vector space x. Okay. So, let u1 u2 belong to x. Okay. So, the this is general definition in any vector space. So, u1 u2 are said to be linearly independent if a1 u1 plus a2 u2 equal to 0 implies a1 equal to a2 equal to 0. The only thing we have to remember here is what is meant by this. So, this is 0 in x. Okay. So, a1 u1 plus a2 u2 is again a function from the interval I into real numbers. So, left hand side is a function and this is the 0 function. So, this means, so this implies a1 u1 t plus a2 u2 t equal to 0. Now, these are real numbers for all t in the interval I. Okay. So, whenever this happens, if that implies a1 equal to a2 equal to 0, then u1 and u2 are said to be linearly independent. Okay. So, otherwise u1 u2 are linearly dependent. Okay. So, now we are going to get some sufficient conditions on u1 and u2 for them to be linearly independent. Okay. So, that is the next next thing. So, so suppose a1 u1 t a2 u2 t is 0 for all t in I. So, u1 and u2 I am picking two functions and suppose their linear combination is 0. Okay. So, when can I conclude a1 equal to 0, a2 equal to 0? That is my question. Okay. So, for this purpose pick t1 t2 in I and t1 different from t2. So, pick any two distinct points and from this now if you substitute t equal to t1 and t equal to t2 because that is valid for all t in I. So, therefore, I have a1 u1 t t1 plus a2 u2 t2 t1 equal to 0 and a1 u1 t2 plus a2 u2 t2 equal to 0. And now, look at these two linear equations, they are homogeneous because right hand side is 0 and consider that matrix u1 t1 u2 t1 u1 t2 u2. So, if okay, so here a sufficient condition if the matrix u1 T1, U2 T1, U1 T2, U2 T2. So, this is the coefficient matrix is non-singular, then it follows that because these are two homogeneous equations and the determinant is non-zero, that matrix is non-singular, it follows that it has only trivial solution A1 equal to A2 equal to 0. So, with this condition, so if we are able to pick two distinct points in the interval I such that if this matrix is non-singular, then we are getting A1 equal to A2 equal to 0. So, that implies U1 U2 are linearly independent. So, let me shorten it. Okay. So, that is only a sufficient condition. It does not appear to be necessary, but in this class X is a huge class of functions. So, it is difficult to find an example, you can try that. So, converse may not be true. So, I just make a remark. So, you may check that may converse may or may not be true. So, I am not sure about that because that class is too big to may not be true. So, what I am trying to say is, suppose you pick any two distinct points in the interval I, and suppose for all the choices if this matrix is singular and yet the functions U1 and U2 are linearly independent. So, that you can, so this question I put a question mark. Okay. But when we take special functions, okay, so we are going to now take a subset of x, then we can say much more. Okay. That is the next thing we will go. So, consider C1I. C1I. So, this is a subset of x. So, I am so these are ones continuously differentiable functions. Okay. So, this class is much smaller than x. Okay. And now again let us study when two functions are linearly dependent or independent. The previous discussion we just took two functions. You can also consider any finite number of functions and discuss their linear dependence or independence, and that algebra will be more complicated, but the same idea. So, instead of two distinct points you have to consider n distinct points and do that. Okay. So, again let me just restrict the discussion to two functions. So, let U1 U2 belongs to C1I and A1 U1 plus A2 U2 equal to 0. So, I would like to see under this condition when and imposing some conditions on U1 U2 if necessary, when does it follow that A1 equal to A2 equal to 0, that means U1 and U2 are linearly independent. In this situation when they are both differentiable, so we get the second equation automatically. So, just differentiate this. So, my differential notation is a dot A1, A2 are just constants. So, when I differentiate the first equation, I get that. So, dot is remember d by dt. Okay. Now, you fix one T naught, pick any T naught in I, then we have this A1 U1 T0 plus A2 U2 T0 equal to 0, and A1 U1 dot T0 plus A2 U2 dot T0. So, unlike in the previous situation, now just one point will do, and we are getting again two equations, and from this we would like to conclude A1 equal to A2 equal to 0, and for that this coefficient matrix should be non-zero. So, this matrix, so if again this U1 T0 U2 T0 U1 dot T0 U2 dot T0 is non-singular, it follows that A1 equal to A2 equal to 0. Okay. And this matrix is called Wronski matrix of U1 U2 at the point T0. Okay. And its determinant, let me write here, determinant is called Wronskian. So, we will introduce some notation Wronskian of U1 and U2 at t equal to 0. So, let me just again write that thing. So, put W U1 U2 at T0 equal to determinant of this matrix U1 T0 U2 T0 U1 dot T0 and U2 dot T0. Okay. So, what we saw in the previous slide is that, so if W U1 U2 T0 is not 0, then U1 U2 are linearly independent. So, when you put more structure into the functions, for example, here we have taken differentiable functions. So, we see a simple condition, and that to just at one point. So, even if the Wronskian is non-zero at one single point, those two functions U1 and U2 are going to be linearly independent. However, converse may be false. May be false, meaning so there exist functions U1 U2 such that W of U1 U2 at t is 0 for all t in the interval, whichever interval we are considering, but U1 U2 are linearly independent. Okay. So, this on striking example. So, let me just mention that. So, example, so you work out the details. So, I is some interval containing both positive and negative real numbers, say for example -1 and 1, okay, and u1 t is t cube and u2 t is mod t cube. Okay. So, this is for t belongs to I. Okay. So, you readily see that u1 is differentiable. So, you might have some trouble seeing that u2 is also differentiable. So, let me just mention here that. So, u1 dot t, that you easily do it. So, this is just 3 t square. So, u2 dot t, simple exercise. So, this is 3 t square if t is positive. Just you break this into several regions. So, you will see that if t equal to 0 and minus 3 t square if t is negative. Okay. So, it is it's something 3 t square, but the sign changes, that is important, and using this definition and this computation you see that Wronskian of u1 u2 t is 0 for all t in I. Okay. However, we show that u1 u2 are linearly independent. Okay. So, for that, so let a1 u1 t plus a2 u2 t is equal to 0 for all t in I. So, in particular you pick t equal to +1, you get a1 plus a2 equal to 0, and if you pick t equal to -1, you get minus a1 plus a2 equal to 0, and this will imply a1 equal to a2 equal to 0. Okay. So, such examples do not occur for some special solutions, again some special functions. So, these are so this is remark. So, you are going to see this in the study of linear second order equations. So, consider this second order equation. So, u double dot plus p t u dot plus q t u equal to 0. So, linear homogeneous equation of second order. So, in some interval, let me again just write any interval. So, if u1 u2 are solutions of this equation, then their Wronskian u1 u2 at any t, okay. Their Wronskian, okay. That is a function is either identically 0 or never 0. So, if it is 0 at one point, then it has to be 0 everywhere, and if it is not 0 at one point, then it has to remain non-zero, and this happens only for this u1, u2 are solutions of this homogeneous. So, that is special functions, and further u1, u2 are linearly independent if and only if, see earlier we proved, if that is Wronskian is not 0 even at one point, then u1 and u2 are linearly independent. Now, here it is if and only if. Okay. So, we saw through this example this converse may not be true, but when u1 and u2 are solutions of this homogeneous second order equation, then converse is also true if and only if their Wronskian is not 0. So, that is an important thing you are going to learn in the study of the second order linear equations. Okay. So, now we move on to the calculus lemma. So, that is the next so, let me state it. So, this is what I have in mind. So, this we are going to need in the study of qualitative analysis of nonlinear systems. So, let chi be a real valued function defined on the interval a b, and again this may be finite, infinite, it does not matter, this interval finite or infinite. Finite or infinite, satisfy. So, these are the assumptions on the function chi either one of these two. Chi is bounded above in that interval, and chi is non decreasing. Or chi is bounded below and chi is non increasing. Then limit chi t as t tends to b. So, b could be infinity. Okay, so, it does not matter, exists. This limit exists means it is a finite number, finite real number. Okay. So, quick proof. So, assume 1. Okay. So, 2 is similar, and in fact, if chi satisfies 2, then minus chi satisfies 1. Okay. So, if limit chi t exists, then limit minus chi t also exists. So, it is sufficient to prove the lemma in one case. Okay. Since chi is bounded above, so put alpha is equal to supremum chi t, t belongs to a b. and since we are assuming chi is bounded above, so this is finite. Okay. So, for any epsilon positive, so now we are going to show that the limit exists for any epsilon. So, if you consider alpha minus epsilon, alpha minus epsilon is not supremum of chi. So, therefore, there is at least one point in the interval where that alpha minus epsilon will be strictly less than chi of t 0. So, for any epsilon there exists t 0 in the interval a b such that alpha minus epsilon, this is no more supremum. So, this should be less than chi t 0. Okay. And now, we use the second hypothesis. So, if t belongs to a b and t bigger than or equal to t 0, then since chi is non decreasing, so chi of t naught is less than or equal to chi t. So, if you put together the previous inequality, so therefore, we have alpha minus epsilon less than chi t 0 and that is less than or equal to chi t, and alpha is the supremum of all chi t belonging to a b. So, this is automatically less than or equal to alpha. So, for all t bigger than or equal to t 0. Okay. So, if you rewrite this thing, so just remove this chi t 0. So, this implies alpha minus chi t, which is always bigger than or equal to 0, is less than epsilon for all t bigger than or equal to t. And this is same as saying that. So, therefore, limit chi t as t tends to b exists and equals to alpha. Okay. So, that is very simple thing, but very useful one. So, this we will see in many situations. And next we are going to discuss about this differentiation under integral sign. Okay. So, for this recall again from fundamental theorem of calculus. So, if f from a b to r is continuous, and if we define f of t, the indefinite integral a to t f s ds, then f is differentiable and f prime t is equal to f t. So, what I am going to state is a generalization of this. Okay. So, where so this you remember. Okay. This you remember. So, this a generalization of this. Okay. Now, so again let alpha beta from some interval a b to r be differentiable functions functions, and f is a function of two variables. So, T S. So, T belonging to A B, okay, and S belonging to this interval alpha t beta t. Okay. In this notation usually you assume that alpha t is less than beta t. So, if beta t happens to be less than alpha t, then you interchange it, or beta t alpha t. Okay. So, there is no restriction on the values of alpha and beta. So, alpha t at some t alpha t can be less than beta t, at some other t beta t can be less than alpha t, that does not matter. Okay. Be a continuous function of both the variables, and I am just taking partial derivative of f with respect to the first variable is also continuous. So, since we are essentially using Riemann integration, so these hypotheses are needed, is also continuous. Okay. So, these are the hypotheses on these functions alpha, beta and small f. So, define, now I am going to define a function of t alone, f of t, just like in the previous case, but now with all these things. So, integration is also, the integral limits are now variables alpha t beta t, and I am going to integrate with respect to s. Okay. So, remember that t is also, t is just fixed. Okay. So, once you fix this t, so this you define for t in A B. Okay. So, then f is differentiable and so this is the formula. It is not really difficult to prove it, just like you do in the previous case. You write f of t plus h minus f t by h, and then you manipulate the integral limits, you will get it. So, it is not at all hard. So, this is alpha t beta t df by dt. So, now I am assuming that is continuous. So, this integral makes sense. Okay. And now, since the limits are themselves variables, so we get some additional terms, and these are like this t beta t dB by dt. And since this is in the upper limit, it comes with a plus sign, and alpha t is in the lower limit, that comes with a negative sign. T. d alpha by dt. Okay. So, just, and this is very useful when you study boundary value problems. Okay. And the next topic of discussion is Taylor's formula. So, let me again start with one variable. That is very familiar with you, to all of you. So, let f from some interval a b to r be a C2 function. So, I am assuming now f is twice differentiable and that second derivative is also a continuous function, okay, and you fix some x 0 in a b. So, using mean value theorem and other things, okay. So, it is not difficult to see that f of x 0 plus y is equal to f of x 0 plus f prime x 0 y plus f double prime, let me just write j y square. So, this j is a point between x 0 and y. So, because we are assuming it is a C2 function, so when y is small, so this quantity is bounded and usually we write that as, okay, f of x 0 plus f prime x 0 y plus O of y square for y small. Okay. And this is very much used in linearization of nonlinear equations. And now, once we have this for one variable case, we will see how to extend it for multivariable case. So, again let me start with one real valued function, multivariable case. In fact, we reduce it to the one variable case. So, let D belonging to R n be an open set and f not same as that f, now it is defined on this D to R be a C2 function. So, in this case C2 function means, so all the first order partial derivatives and second order partial derivatives with all the variables, n there will be n variables, they all exist and they are continuous. Okay. So, again let x 0 belong to x and not x D, and you choose a small ball. So, since we are assuming D is open and choose R positive such that B x 0 R is also contained in D. So, D will be something like that, x 0 is here and I am just taking a ball of radius R, that is fine. So, now we are just picking y there and trying to so pick any y, pick y in B x 0. Okay, so define. So, this is now f is from D to R. So, now I am going to define a one variable function. So, this is f of x 0 plus t y. Okay. So, t is between 0 and 1. Okay. So, now if you apply the one variable case, so with y equal to 1 and x 0 equal to 0. So, therefore, we have f of 1 is equal to f of 0 plus f prime 0 into 1. So, that is fine, and now f double prime xi, and xi is between 0 and 1, f double prime. Okay. So, just try to ignore this second order derivative, we are not interested, again that is bounded. So, we are going to, so we are just interested seeing the linear terms. Okay. So, let us calculate what f 0 is and f prime 0. So, f 0, if you look at the definition of the capital F function. So, f 0 I put t equal to 0 there. So, this is just f of x 0, and what is f 1? F 1 is f of x 0 plus y. Okay. And by chain rule, f prime t, let me just write f prime t. So, so this is a function of n variables. So, by chain rule, so this is just del f by del x j evaluated at x 0 plus t y into the differentiation of this argument with respect to t, and there is only dependency is through this t y. Okay. So, we just get y j. Remember, y is a vector. So, this is just y j equal to 1 to n. So, since we are in n variable case, that happens. So, f we are interested in f prime 0. So, therefore, f prime 0 is del f by del x j, t equal to 0 means just x 0 y j, and this you can write in the notation of gradient. So, this is gradient of f at x 0 dot y. So, this is a vector and that is a vector. So, this is a scalar product. Okay. So, this is gradient. Okay. So, therefore, if you put back x 0 plus y f of x 0 plus gradient of f at x 0 dot y plus, let me just write that as y square. Okay. So, we are interested only in the linear terms, and now you can just extend it to many variable case. Again, let d be as before, and now let f from d to r n. So, you can also do it for r m. So, let me just for simplicity do just for r n, and then f will have n components. Okay. So, f 1, f 2, f n, and each f j is now from d to r. And now we can apply the previous discussion with this, apply the previous formula in this for Fj, and if you do for all Fj, then so we have this, then you put together we have this f of x 0 plus y. Now this is a vector, so this is also a vector. So you should get a vector here, but y is only a vector. So the that if I want to get a vector out of that, so you should multiply by a matrix, and this is just y. So this is n by n matrix, and this is called Jacobian of F. And if you look at the previous formula and apply to each Fj, so this df x 0 is nothing but, so it is a matrix, and each row is gradient f 1 at x 0, and you have gradient f n x 0. So you write the gradient as a vector. So the first vector coming from f 1, second vector from f 2, etc. So this is a matrix. So this is n by n matrix. Okay. So finally, let me quickly discuss this fixed point theorem. Okay. For this we need the notion of a metric space. So let x be a non-empty set, a function d from the Cartesian product to R is called a metric or distance function. If it satisfies the following three properties. So if you take any 2 points in x, so their distance is always non-negative and equal to 0 if and only if x equal to y. This property is referred to as positive definiteness, and second one is symmetry. So distance from x to y is same as distance from y to x, symmetry. And third one is called triangle inequality. So d of x y is less than or equal to d x z plus d z y. So these three properties should hold for all x, y, z in x. Okay. And so this again, this notion comes from the Euclidean distance. So this is for example in R, if you take x equal to R and the distance defined by the usual Euclidean distance, so that is a metric. And in Rn again the standard Euclidean distance. So these are examples of metric spaces. Okay. Yes. So x d, so x is a non-empty set and d is a metric on x is referred to as a metric space. So we have another few minutes. So, let me just a sequence x n in X is said to be a Cauchy sequence if limit. So, remember this, when you put d, so these are all real numbers now, x m x n, and this should go to 0 as m n goes to infinity. Okay. You can also write it in form of epsilons. Okay. A sequence x n converges, x n in X converges to some x in X if d x n x tends to 0 as n tends to infinity. So, a metric space is said to be a complete metric space if every Cauchy sequence in X converges to some point in X. So, it is easy to check if a sequence converges to some X and that X is unique. So, a sequence cannot converge to 2 elements in X. Okay. So, that limit is unique. So, now we are going to state this fixed point theorem Banach fixed point theorem. So, let x d be a complete metric space. So, completeness plays an important role. So, without completeness, the conclusion of this theorem may be false. And T from mapping from X into X itself be a contraction. So, that is, so I am going to define what is contraction. So, if you take any 2 points x and y in X and now you take their images under T. So, T x T y are their images and you compute the distance between them, and this should be less than or equal to alpha distance x y. So, for some 0 less than alpha less than 1 and all x y in X. The conclusion is then T has a unique fixed point. that is there exists x star in X such that T x star is equal to x star, and x star is unique in with this property. So, that is meant by that unique fixed point. Okay. As a corollary, so let again same setting. So, let T from x to x be such that, so T need not be a contraction, but what we are assuming is T to the n is a contraction. So, T to the n means you compose T with itself n times. So, T square is T composite T, etc. is a contraction for some n bigger than or equal to 1. Then T has same conclusion, unique fixed point. Okay. Let me indicate how this corollary follows. So, proof of the corollary. Okay. So, since T n is a contraction, we apply Banach's theorem. So, there exists unique x star such that T n x star is x star. Okay. So, because T n is a contraction, we are assuming T n is a contraction, and this implies if I again compose with T, so T n of T x star is equal to T x star, and by uniqueness, so this is by uniqueness, T x star is equal to x star, because x star is unique. Now, we are showing that T x star is also a fixed point for T n, and that is why we should have this T x star equal to T x star. And further if T x is equal to x for some x, so if T has another, so that implies T n x is again x, and that again by uniqueness implies x equal to x star. Okay. And especially with this hypothesis of the corollary is very useful, that you are going to see in the existence of solutions of differential equations. That is very much useful. Okay. So, with this thing we will conclude this lecture on some preliminaries. Thank you.